Welcome back to the deep dive. Today we are really getting into the bedrock, the architecture of modern intelligence.
That's right. We're diving into modeling, data science, and machine learning.
And look, if you've ever felt a bit lost with terms like supervised learning or, transformer architecture, this is for you.
Definitely. Our mission today is pretty straightforward. Give you the essential terms, the standard process professionals actually use, and a handle on the really cutting-edge concepts driving automation.
We want to cut through the complexity, basically, so you can feel confident in any technical discussion.
Exactly. Let's start right at the beginning, foundational stuff. When we talk about building intelligence, we're creating representations of reality. Models.
Right, models. But models need something to represent a system. What exactly is a system in this context?
Good question. So a system is basically an organized collection of elements. They're connected, they interact, they have goals, procedures, and the model. It's just a representation of that system. Often it's a mathematical description of, how things are or how they work.
And the key insight, especially for dynamic systems, things that change, is that we really need to lean on computer models, simulations, not just our own sort of mental picture of what might happen next. Why is that step so important?
Yeah, that's critical. It really boils down to objectivity. Our human mental models, they're full of biases, faulty memories, shortcuts. Computer models, running simulations, they strip that away. They aim for objectivity. And these models, they serve, broadly speaking, 4 key functions.
Okay, what are those?
Estimation, prediction, which is about forecasting future values, calibration, kind of linking measurements across different systems, and finally, optimization.
Optimization. Finding the best way to get a desired result.
Precisely, finding the best inputs to get the outcome you want.
Okay, so we know why we build models, but how does the actual work happen? It can't just be like random coding, right? There must be a process.
Yeah. Oh, definitely not random. Because data science is fundamentally aimed at solving, real business problems, there's a globally adopted standard roadmap. It's called CRISP-DM.
CRISP-DM. What does that stand for?
It's the cross-industry standard process for data mining. Think of it as the blueprint for any serious data science project.
A blueprint. I like that. It gives structure. So what are the steps? The first couple seem pretty logical. Phase 1, understanding the business problem. What are we trying to achieve?
Correct.
And phase 2, understanding the data. What have we got to work with? Is it any good?
Exactly. Check the quality, see what's available. But then comes the really heavy lifting. Phase 3, data preparation.
Okay. What's involved there?
This is the cleaning, the organizing, selecting the right variables, basically getting the raw data into shape. And here's the kicker, the thing that often surprises people.
Yeah.
Industry analysis consistently shows this one-phase data prep can eat up, up to 80% of the entire project's time.
80%. Just prepping the data.
80%. That's the critical nugget, the practical reality check. It's not always the fancy algorithms that take the longest. It's the data scrubbing.
Wow. Okay, so that 80% rule is key. After you climb that mountain, what's next?
Right. Once the data's clean, you move into phase 4, which is modeling. This is where you actually build and test different algorithms.
Yeah, test them, right.
Then phase 5 is evaluation. You look at your results and decide which model performed best based on the success criteria you set way back in phase 1.
Makes sense. Compare against the goal.
And finally, phase 6, the finish line, is deployment. Getting the results, the insights, the model out into the real world where it can be used.
And not just deploying it, but planning how to keep it running, right? Monitoring and maintenance.
Absolutely crucial. Deployment isn't fire and forget. These systems need ongoing care.
Okay, so that modeling phase, phase 4, heavily involves machine learning or ML. Where did that term even come from?
It's actually quite old, coined back in 1959 by Arthur Samuel.
Wow, okay. But I think the definition that really clicks, for me anyway, is Tom M. Mitchell's. It defines learning by observing improvement.
Right, the P, T, and E.
Yeah. A computer program learns if its performance, P, on a specific task, T, gets better with experience, E. It's learning without being explicitly programmed for every single rule.
That's the core idea. Learning from data, from experience. And this learning ML, it generally breaks down into 3 main types, 3 pillars based on the kind of experience the machine gets.
Okay, 3 pillars. What's the first one?
The first is supervised learning. The name gives it away. There's a supervisor or a teacher.
Maybe you give it examples of the answers.
Exactly. Labeled data, here's the input, and here's the correct output we want you to learn.
Okay. And what kinds of problems does that solve?
Primarily two main types. Classification, which is about sorting things into categories like, is this email spam or not spam? Yes or no.
Got it. Categorical answers.
And the other is regression, where you're predicting a continuous numerical value. Think predicting house prices or next quarter's sales figures.
Right, predicting a number. Okay, so that's supervised learning. What's pillar number 2?
Pillar 2 is unsupervised learning. Here, there's no teacher, no labels.
So you just give it data.
You just give it a whole bunch of unlabeled data, and the algorithm's job is to find the hidden patterns, the structure, the relationships within that data all by itself.
Interesting. What are the main techniques there?
Well, a big one is clustering, grouping similar data points together automatically, like finding different customer segments in marketing data.
Oh, okay. Grouping things.
Another really important one is dimensionality reduction. This is about simplifying complex data by reducing the number of input features, but crucially, without losing the essential information.
Simplifying the input. Gotcha. Okay, pillar 3.
The third pillar is reinforcement learning. This one is quite different. It's learning through feedback, kind of like how you might train an animal.
Through rewards and punishments.
Pretty much. An agent, the algorithm, learns by trying things out in an environment. It takes actions. And based on whether those actions lead to a good outcome, a reward, it adjusts its strategy, its policy, to maximize the total rewards it gets over time.
So it learns the best strategy through trial and error. Where is this used?
Think complex robotics, game-playing AI situations where the optimal path isn't known upfront.
Right. And you also mentioned hybrid forms, like ensemble learning.
Ah, yes, good point. Ensemble learning isn't really a separate pillar of learning from data in the same way. It's more a technique.
How does it work?
You basically train multiple different models on the same task, and then you combine their predictions, like having a committee of experts vote on the final answer.
Ah, safety in numbers for algorithms.
Kind of. It often leads to more robust and accurate results than any single model could achieve alone. Techniques like bagging and boosting fall under this.
Okay, so when we're evaluating these models back in phase 5 of CRISP-M, what makes a good model? What are we looking for?
Ideally, we want a model to have 4 key characteristics. First, simplicity.
Simplicity. Why simple?
Because simpler models are usually easier to understand, to interpret, and they tend to be more robust, less likely to break on unexpected new data. It links back to that old principle, Occam's razor.
Occam's razor, the simplest explanation is usually the best.
Essentially, yeah. Choose the solution with the fewest assumptions, all else being equal.
Okay, simplicity. What else?
Second, accuracy. Does it actually predict well on the data we trained it on? Third, robustness. This is crucial. Does it predict well on new, unseen test data? Data that's different from what it learned on.
Right, needs to generalize.
Exactly. And fourth, scalability.
Yeah.
Can the model handle growing amounts of data efficiently without needing, exponentially more time or memory?
Simplicity, accuracy, robustness, scalability.
Got it. But you mentioned attention.
Ah, yes. The fundamental challenge. You almost never get all 4 perfectly because of something called the bias-variance tradeoff.
Bias-variance tradeoff. Okay, break that down. So bias refers to the errors from making overly simple assumptions. If your model is too simple, it has high bias. It doesn't really capture the underlying patterns in the data. We call this underfitting.
Underfitting.
Too simple. On the other hand, variance refers to errors from being too sensitive to small fluctuations in the training data. If your model is excessively complex, it has high variance. It starts modeling the random noise in the training data, not just the signal.
That's bad because
it won't perform well on new data. It's learned the noise specific to the training set. This is called overfitting.
Overfitting. Too complex, learns the noise. So it's a balance between too simple and too complex.
It's exactly that, a constant balancing act. You want a model complex enough to capture the real patterns, low bias, but not so complex that it learns the noise, low variance. Finding that sweet spot is key.
So if overfitting is the big risk learning noise, why not always just make models super simple, lean towards high bias?
Because, well, reality usually isn't that simple. A model that's too simple, too biased, just won't be accurate enough to be useful for most real-world problems. You need enough complexity.
Right. Okay, besides that fundamental trade-off, what are other big challenges?
Well, the whole CRISP-M process itself is complex with that huge data prep phase. But technically, a major hurdle is the curse of dimensionality.
Curse of dimensionality. Sounds dramatic.
It kind of is. It refers to the difficulties that arise when you have a very large number of input variables or dimensions. Optimizing a model becomes exponentially harder.
More data, more problems.
In a way, yes. There's even a related idea called the Hughes phenomenon. Adding more features initially helps performance, but only up to a point. Add too many features, and performance actually starts getting worse.
Wow. So more information isn't always better. How do we fight that curse then? How do we improve models?
There are several strategies. One is property or feature engineering. This is about creating better input features from the raw data. Maybe transforming variables, like using logarithms, or encoding categorical data numerically, like with one hot encoding.
Making the input smarter.
Exactly. Another is property or feature selection. Instead of creating new ones, you strategically remove less important or redundant features. Techniques like PCA or stepwise regression help here.
Okay, selecting the best inputs.
Right. And then there's ensemble learning, which we mentioned, combining models, and also pairful hyperparameter optimization.
Hyperparameters. Those are the settings of the learning algorithm itself, right? Not the model parameters learned from data.
Precisely. Things like the learning rate or the complexity of a model, tuning these effectively, often using techniques like cross-validation, is critical for getting the best performance.
Let's shift gears now to the really cutting-edge stuff. Deep learning, DL. How does this fit in with machine learning?
So deep learning isn't a fourth pillar or anything. It's actually a specific branch of machine learning. It's based on artificial neural networks, ANNs.
Neural networks, okay. And the deep part.
The deep refers to the structure of these networks. They use multiple layers specifically, multiple internal or hidden layers stacked on top of each other. This depth allows them to learn progressively more complex patterns and build layers of abstraction from the data.
So more layers means deeper learning. How do these ANNs work at a basic level?
Well, the basic unit is the neuron or node. Think of it as a small computational unit. It receives input signals from other neurons.
Okay.
Each connection has a weight associated with it, representing its importance. The neuron sums up these weighted inputs and then applies a nonlinear activation function to decide whether and how strongly to fire its own signal forward to other neurons.
Weights and activation functions. And the learning part is adjusting those weights.
Exactly. The whole learning process is about iteratively adjusting those millions, sometimes billions, of connection weights throughout the network to minimize the difference between the network's output and the desired output, basically, to reduce the error.
And for supervised learning, how does the network know how to adjust all those weights when it makes a mistake?
Ah, that's the magic of backpropagation.
Backpropagation. Sounds complex.
The core idea is relatively simple, though the math can get intense. When the network produces an output, you calculate the error how far off it was. Backpropagation is an efficient algorithm to send that error signal backwards through the network, layer by layer.
Sending the error back.
Yes, and as it goes back, it calculates how much each connection weight contributed to the error. Then, it adjusts each weight slightly in the direction that reduces the error. It's like assigning blame and telling each connection how to fix itself.
Okay, so it's an efficient way to update the weights based on errors, and you mentioned tensors.
Right. Tensors are just the fundamental data structure used in deep learning. Think of them as multidimensional arrays. Scalars are 0D tensors, vectors are 1D, matrices are 2D, and you can have 3D, 4D, and so on. All the data inputs, weights, outputs flows through the system as tensors.
Got it. Tensors are the data containers. Now, let's talk architecture. There have been some major innovations in neural network design. What are the key ones?
3 stand out. First, CNNs, or convolutional neural networks.
CNNs. I hear about those mainly with images.
That's their primary domain, yes, though they're used for text too. The breakthrough with CNNs is that they don't just look at individual pixels independently. They use filters, also called kernels.
Filters or kernels, what do they do?
Think of them as small windows that slide across the input image, looking for specific patterns, edges, corners, textures. They automatically learn which patterns are important. And CNNs also use pooling layers. Pooling layers basically shrink the image representation down, making it more manageable and, importantly, helping to control that overfitting problem we talked about by making the network less sensitive to the exact location of features.
Okay, so CNNs for spatial hierarchies, like in images. What's next?
Next up are RNNs, recurrent neural networks. These were specifically designed for sequential data.
Sequences,
Yeah.
like time series data or sentences in natural language.
Exactly. The key innovation in RNNs is the concept of a hidden state, which acts like a memory.
Memory. How?
The output from processing one element in the sequence, like a word, is fed back into the network as part of the input for processing the next element. This loop allows the network to maintain information about previous elements in the sequence, giving it context.
So it remembers what came before.
Right. But basic RNNs struggled with long sequences. They tended to forget things from too far back. That led to the development of more advanced types, specifically LSTM, long short-term memory, and GRU, gated recurrent unit.
LSTM and GRU. What makes them better?
They have internal gates, sophisticated mechanisms that control the flow of information. They learn what information to keep in memory, what to forget, and what to output, allowing them to handle much longer dependencies and sequences.
Smarter memory management. Okay. And the third big one, the one everyone talks about now.
Ah, yes, the current king of the hill. Transformers, or TNNs.
Transformers. What's their big trick?
The absolute game changer with transformers is that they are not recurrent. They don't process sequences step by step like RNNs.
No recurrence. How do they handle sequences then?
They process the entire input sequence all at once. And they do this using a mechanism called attention.
Attention. What does that mean here?
Attention allows the model, when processing one part of the input, say one word, to look at all other parts of the input and dynamically decide which parts are most relevant or important for understanding the current part. It learns contextual relationships across the entire sequence simultaneously.
So it can weigh the importance of different words in a sentence no matter how far apart they are.
Precisely. This ability to capture long-range dependencies, combined with parallel processing, is why transformers have revolutionized fields like natural language processing.
Okay, this is fascinating stuff. But to actually do any of this, you need tools, right? What's in the typical data scientist's toolkit?
Absolutely. For general data manipulation and ML, the Python ecosystem is dominant. Libraries like pandas are essential for handling data cleaning, transforming, analyzing.
Pandas for data wrangling. Got it.
And scikit-learn, often just called slurn, provides implementations of, well, tons of standard machine learning algorithms, classification, regression, clustering, dimensionality reduction, model evaluation tools. It's incredibly comprehensive for traditional ML.
Sklearn for the core algorithms. And for the deep learning, the ANNs, CNNs, transformers.
They're the two main players. The major frameworks are PyTorch, developed primarily by Facebook Meta, and TensorFlow from Google.
PyTorch and TensorFlow.
Both are powerful libraries for building and training complex neural networks. TensorFlow often comes with Keras, which acts as a higher-level, more user-friendly interface on top of it, simplifying many common tasks.
Okay, so you build and train your model using these tools.
Bruh.
How do you get it out of the lab and into the real world where it can actually do something useful? Deployment.
Right, deployment. There are a few common strategies. One is batch inference.
Batch, like processing a big chunk of data all at once.
Exactly. You have a large data set, maybe all your customer data, and you run the model on the entire thing periodically, perhaps overnight, to generate predictions. This often happens in the cloud.
Okay, batch processing. What else?
The second is online or real-time inference. This is for applications that need immediate predictions.
Like fraud detection on a credit card transaction.
Perfect example. The model needs to accept a single request the transaction details and return a prediction, fraud not fraud, almost instantly. This is often done by exposing the model via a REST API.
API for instant answers. And the third way?
The third is embedding the model directly onto a device.
On the device itself, like on a smartphone.
Yes, or an IoT device, a car, whatever. This is crucial for applications that need to work offline or require very low latency. Frameworks like TensorFlow Lite are designed specifically for optimizing and running models on these resource-constrained devices.
Right. Makes sense. Now, deploying these powerful models, especially complex ones like deep neural networks, brings up a huge issue. Trust.
Absolutely critical. If a model is making important decisions, loan applications, medical diagnoses, autonomous driving, we can't just accept its output without understanding why. It can't be a complete black box.
Which leads us to explainable AI, or XAI.
Exactly. XAI is a whole field dedicated to developing techniques that help us understand and interpret the predictions of machine learning models. It's becoming non-negotiable for robust, ethical deployment.
So how do we peek inside the black box? What are some XAI techniques?
There are quite a few. One approach is the partial dependence plot, PDP. It shows, on average, how the model's prediction changes as you vary one or two input features while holding others constant.
So it shows the general trend for a feature.
Right. But sometimes you want to know why a specific prediction was made for one individual case. For that, you might use individual conditional expectation, ICE plots. They show how the prediction for a single instance changes as you vary a feature.
Okay, you get more specific.
And perhaps one of the most popular methods right now is based on Shapley values. Often implemented in libraries like SHA, it comes from game theory, actually.
Game theory, how does that apply?
It calculates the marginal contribution of each feature to the specific prediction for a given instance. It tells you exactly how much each input factor pushed the prediction higher or lower from the average. It gives you feature importance at the individual prediction level.
Wow, okay. That sounds really useful for debugging and building trust. So given all this complexity, the multi-phase crisp DM, the complex models, the need for XAI, it sounds incredibly labor-intensive.
Mhm.
Is there a move towards making it easier?
Yes, definitely. The big trend addressing this complexity is automated machine learning, or AutoML.
Automating the automation.
Pretty much. AutoML tools aim to automate many of the tedious and time-consuming steps in the machine learning pipeline. Things like data preprocessing, feature engineering, feature selection, model selection, and especially hyperparameter optimization.
So it tries out different approaches automatically.
Exactly. Tools like AutoSclern or TTOT automatically explore many different models and configurations to find the best performing pipeline for your specific task, saving the data scientist a huge amount of time and effort. Hashtag outro.
Well, that was quite a journey. We went from the basic definition of a system and a model through the entire CRISP-DM process.
Highlighting that crucial 80% rule for data preparation.
Right. Then we covered the main types of machine learning, the fundamental bias-variance trade-off.
And dove into the architecture of neural networks, CNNs, RNNs, and the game-changing transformers with their attention mechanism.
Plus the tools, deployment strategies, and the critical importance of explainable AI.
Hopefully, you now have a solid grasp of the key concepts and the vocabulary. Whether you're in tech, finance, research, or just curious about AI, understanding this blueprint is increasingly valuable.
It really provides a framework for thinking about how data is turned into insights and actions.
Definitely.
So let's end with a thought to mull over. We talked about simplicity Occam's razor as an ideal characteristic for models. Yet the clear trend, especially with deep learning and AutoML, is towards greater complexity and automation.
That's true.
So here's the question. As models get inherently more complex and automated, does striving for simplicity remain the most important guiding principle? Or has interpretability, being able to explain why a model does what it does via XAI, become the truly essential requirement for building robust, trustworthy AI systems in the real world?
That's a fantastic question. Simplicity versus interpretability in the face of growing complexity. It's something the field is actively grappling with.
Something for you to think about. Thanks for diving deep with us today.
Thanks, everyone.
I'll see you next time.